All right, good morning, everybody. We're going to continue talking about some topics from Chapter 5 today, the Reynolds transport theorem, and how we can use that for problem solving related to reservoirs. I've handed back the quizzes, and I had the solution up on the screen there for a few minutes before class. And so if you have any question with what you did or how your quiz was graded, feel free to stop by during my office hours, and I'd be glad to go over it with you. That's the last quiz for the semester. Of course, we still have exam 2 and the final exam, so there's still plenty of points out there on the board to be earned. The next homework assignment, homework 8, that's available right now on Blackboard, and that assignment's due on Tuesday. Chapter 5 is mostly about Q equals VA, or various variations of it, mass flow rate is density times Q. So it's fairly simple concepts, but I'd encourage you to get an early start on this assignment just in case you run into any trouble interpreting the problem statements. In a couple of cases, those are word problems that I didn't make it vague or confusing on purpose, but I intentionally set it up so it wasn't the simplest way I could have said it. I could just always define the variable for you, and all you have to do is put it into the equation. But I think it's good practice to learn to pick out the variables from a written description of the project, because that's what you'll be doing in a lot of cases after you graduate. So that assignment's available now. Any questions on the announcements? All right. Last time in class we looked at the case of a tank that had a pipe flowing in and a pipe flowing out, and we talked about some technical definitions related to a system of particles. And a system of particles is just a certain number of particles that we identify from the beginning as being part of our system, and there can be identical fluid particles on either side of the system. So this could be a water tank with water flowing in and out, but we just say, this dark blue is what we're going to designate as our system. And the reason why we do that is we consider it as a tracer that we're going to keep track of over time and monitor the amount of the system in each of the inflows and outflows so that we can understand the accumulation inside of a control volume. So remember that when we talked about control volume, or CV, that was defined as an enclosed space that has potentially the capacity for storage, and CS, control surface, was the outside surfaces that fluids can flow through in order to go in and out of the control volume. So our book goes into a pretty lengthy explanation of Reynolds transport theorem, and we'll just take a quick taste of that. What the Reynolds transport theorem says broadly is that we have two components, a storage term and a transport term. And in the storage term, what we're considering is what's going on inside of the control volume. So you see here, what this says is that the change over time of the mass in the control volume, and so the way that we get mass is by having some change in volume. The V with the cross through the center of it, that is to be distinguished from this V, where the V with the line through it, that is volume. And just the other V, if you see both in an equation, the other one would be velocity. And so in the storage term, this is saying what we're keeping track of is some change in volume over time in the control volume. And if we multiply that change in volume by the fluid's density, then we turn that into a change in mass over time. And so between two time periods, in the illustration we looked at on Tuesday, since the liquid level fell between T and T plus delta T, the liquid level was a little bit lower. That's how we knew that the change in storage during the time period was negative. The mass decreased. So the other part of the Reynolds transport theorem is the transport term. And so what the transport is concerned with is the flow through the control surfaces of velocity. And so it can be a flow of gas, it can be a flow of a liquid, but through some differential cross-sectional area, so maybe it's the cross-sectional area of the inflow pipe, the cross-sectional area of the outflow pipe, if we know the velocity of those streams and multiply it by the area. And it may be that we just use an average velocity and we have the overall cross-sectional area. Or in some specialized cases, we may have a good equation that defines the velocity profile. And if you have the velocity profile, then you'd actually apply the velocity at some known location to the area that's representative of that location, or we can integrate it if it's continuous. And so V times A, remember, is a volumetric flow rate. And so if we multiply it by the density, now that's a change in mass per time flowing in and out of the system. And so there can be multiple contributing terms to the transport term here. There could be an in and an out that both are considered part of the transport term. Notice in the storage term there's a d dt, but there isn't one for transport. There's one for storage, but not for transport. So why is there not a separate change in time specified for the transport term?
Velocity is going to remain constant.
Okay, velocity. We already have our time parameter defined by the velocity. You know, here in the storage term there was density, which doesn't have a time component, and volume. And so if we want to keep track of how things are changing over time, we'd have to say explicitly, and we're tracking how change over time occurs. Whereas in the transport term, area doesn't have a time component, and neither does density, but velocity is length per time. And so that's already built into the transport term. So those two things combined together will tell us the change of mass in the system over time. Now, there could be a reaction that's also happening inside the system. There could be a production reaction if it's maybe a chemical reactor, and some constituents are mixing, you know, two reactants are mixing and a product is being formed. And so it's possible that the mass of a certain thing that we're tracking is increasing or decreasing beyond just storage and transport. It's not that the overall mass of all things combined is going up or down, but we can apply the Reynolds transport theorem just to certain types of mass. And so if you had water but it has other things mixed into it, you could keep track of the Reynolds transport theorem just for those individual subcomponents of a mixed stream. So here are the terms that are defined for the Reynolds transport theorem, and it's not until you get into environmental engineering, or maybe if you ever take a chemical engineering elective, that you'd keep track of the chemical reaction as well as the flow in and the flow out. This semester specifically, we're going to simplify the Reynolds transport theorem to assume that there's no chemical reaction due to the formation or the degradation of components inside the reactor. We'll just be looking at the flow in, the flow out, and the accumulation. And so here's that same equation from the previous slide. The assumption is that when we don't have mass being created or destroyed, so if the change in mass in the system over time is 0, then that just means that the flow in and the flow out is what accounts for the accumulation. So we set that equal to 0, and remember the two terms are the storage term and the transport term. And so what this equation now says is that the change in storage can be explained by the change in transport through the in and the out. That all of this when combined is equal to 0. In other words, I think in class previously I really simplified things and I said accumulation equals in minus out. And so what this is saying is in minus out on one side of the equation, and then we would say, I guess, minus accumulation is equal to 0. So that the difference between the in and the out is going to account for the accumulation, whether it's positive or negative. And so here, if there's more in than out, in order to keep this equation equal to 0, then we would have to be subtracting the accumulation. or if there's more out than in, then the accumulation is going to be decreasing. And so for all of this to be equal to 0, it's a way for us to keep track of the mass inside of the control volume. And so here this is on a mass basis. It's saying the mass flow rate in terms of kilograms per second, for instance, in minus out is how we account for the accumulation of mass inside of the control volume over time. All right. At the beginning of chapter 4, when we were talking about flow visualization and tracking particles, we discussed how the Lagrangian approach is difficult because there are so many particles in a flow field. And so we were comparing and contrasting what we would do for a Lagrangian and Eulerian approach for finding the change in pressure as water flows from one point to another. Now, Euler's equation can be used in a flow field like this. You know, at first glance, this is the type of sketches and drawings you saw when we were doing Bernoulli equation problems. But we can apply Euler's equation just to a single particle. We can't apply it to the entire cross-section, but if we're willing to keep track of individual particles, then a particle is changing its velocity over time. You know, if this is steady state, meaning that conditions aren't changing over time, if it's steady state, then there isn't a change in velocity upstream or downstream over time, but an individual particle that's flowing from A to B, that individual particle is going to have its velocity change over time. So because of that, if you wanted to find out what's the pressure at B, if you know the pressure at A, you could integrate Euler's equation as it applies to a single particle traveling between those 2 points over a known time increment. So that, in other words, there is a local acceleration occurring by a single particle, even when what's happening system-wide is a convective acceleration. More simply, though, we can apply Bernoulli's equation to the entire cross-section, but remember the limitation there is steady flow. One of the limitations. But as before, the challenge with using the Lagrangian approach to saying what's the pressure change between these 2 points is that we can only apply it to individual particles. And there's so many different particles with flow paths that are changing over time, because if we have turbulent flow, it may be that the flow path between A and B is different from one moment to the next. The particle trajectory is constantly changing, and so it may bounce around the walls a few times in its indirect route between A and B. So that raises a lot of challenges, and so remember that the Eulerian idea was let's just divide up the flow field into elements or use a mesh, and then we'll keep track of the flow of properties across that mesh. So this is going to be used for predicting the pressure at a location, because what we would say is we'll look at the change in pressure just across this small element, and then all of the fluid particles that pass through that element are assumed to have the properties of the element itself. So we can look at the forces that apply on either side of the element, including differences in pressure over an area. Remember that pressure times the area is a force, and so when we have a transition like this, if there's more pressure on the side where there's a low velocity and less pressure on the side where the velocity is faster, that's an imbalance of force that we can account for in the shear stress at the edges of the boundary, and also the change in pressure that we want to look for what's the conditions at B. So the book goes into the point that you can use the Reynolds transport theorem not just for keeping track of the mass of fluid as it moves from place to place, but it plays a role in applying the Eulerian approach to predicting pressure. So let's just sort of step back from that more theoretical approach to the Reynolds transport theorem and look at a reservoir again. this is a tank of water that has one stream coming in and one stream going out. And in this case, we know the diameter of the tank. So it's a circular tank that has a diameter of 0.5 meters. And so what's that defining is the distance from one edge of the tank to the other, so we can use it to find the cross-sectional area of the tank. And so this is somewhat related to the in-class exercise that we were working in at the beginning of, at the end of class on Tuesday, that Oahe Reservoir, and trying to find out how long it would take for the liquid level to fall downward. This is a similar thing where we don't yet know if it's going up or down, and so we have the given information that this is water. So of course the density of water is 1,000 kilograms per cubic meter. We know the velocity of the jet as it crosses one of the control surfaces. The velocity of the jet will continue to change. You notice how it's tapered. The diameter of the jet is getting smaller here, presumably because what they're kind of illustrating is that the velocity is getting faster as it falls downward more and more. So the cross-sectional area is also decreasing as the velocity goes up. So here at the control surface, where we have, we're keeping track of the flow in, we know the cross-sectional area of that jet that's going in and the velocity. So what I'd like you to do is take a look at, define m dot for the in, and here we already know the m dot for the out. So what's the rate of accumulation inside of that tank on a mass basis? How many kilograms per second are accumulating positively or negatively? And then what does that tell us about, is the liquid level going up or down? And what's the velocity that the liquid level is going down? And so if we have a circular tank and we know the cross-sectional area, then the velocity that the liquid level goes down, velocity is Q divided by the area. So in the first part of this problem, you're going to find the mass flow rate, the change in mass flow rate over time. And you can put that into volumetric flow rate, Q, because it will be the mass flow rate divided by the density. All right, so I'm going to pause the recording for a moment, give you some time to do the calculations. The two things we want to know is what's the rate of accumulation of mass, so what's the dm in the control volume over time, and then what's the velocity that the liquid level is rising or falling due to the imbalance between in and out. Okay, so if we know the diameter of the tank, we can find the cross-sectional area, meaning the area of the top of the water in that circular tank. But that's not the area we use when we find the flow rate in. The flow rate in is going to be applied to that smaller area of the jet. So if we know the Q in and the fact that this is water, we can find the mass flow rate in is going to be 17.5 kilograms per second. And the flow out is 3 kilograms per second. I guess we know that directly. Change the example slightly. So the net difference between the two is that there's a positive accumulation of mass of 14.5 kilograms of water every second in the tank. So if it's a really large diameter tank, then that means that the water level is going to be rising slowly. So think about a swimming pool. How slowly the water level is rising on a pool because it has such a big cross-sectional area. But if you have a really narrow, like a graduated cylinder, for example, then the liquid level is rising really quickly because of the small diameter, small cross-sectional area. So when we take this mass accumulation and convert it back into volumetric, I guess we could have kept it volumetric all along, but it's good practice just to keep in mind how to adjust between volumetric flow and mass flow. the rate of accumulation on volumetric terms means that in every second that 14.5 kilograms that accumulates is going to be occupying a volume of 0.0145 cubic meters. And so if that's the volume of accumulation, the rate of rise of the water level is the volume of accumulation divided by the cross-sectional area of the tank. So what we should see is that the liquid level is rising at a velocity of 0.0738 meters per second. Yeah.
The diameter of the tank, that was 0.5, right?
That's right. Yep.
So how did you get the area was that number?
Let me go up here. So pi d
okay,
squared divided by 4. Yeah. If you're accustomed to thinking in terms of radius, it's hard to switch over and always remember to this divide by 4. Are there any other questions about the example? I think you've got at least one problem on the homework assignment that's just this same kind of thing, where you look at the difference between flow in and flow out, and then you use the area to find out how quickly it's going up or down. I mean, that's kind of the essence of the example from Tuesday as well, the reservoir. Okay. So, accumulation is in minus out. And if in is greater than out, then that means there's a positive accumulation, and if it's in a storage tank, then the water level will rise. So consider this. We've got two different pistons. Both of the pistons are sliding to the left. Piston A is sliding to the left at 2V. Piston B is sliding to the left at V. And you can see the diameters for each. So just qualitatively, before we do any calculations, do you already have a sense for whether the liquid level is rising, falling, or held steady?
It's rising. Looks steady.
You think steady?
It's rising.
Or he says rising. Anybody think it's falling?
I don't think so. Well, if they're moving at
They're-
V and then 2V,
Right, so this is double the velocity.
but the area is 4 times as big.
Yeah, that's the trick. Yeah. So it's not the diameter. Remember, it's the cross-sectional area. So the first reaction is, well, since it's double the velocity but half the diameter, maybe it's steady. But Q equals V times A. It's not Q equals V times D. And so in this one, the area A is going to be 1/4 the area at B. So just as an illustration of that, let's take a quick look at this one. Okay, so if the area at A is based on the 3 centimeter diameter, then that makes the area approximately 7 square centimeters, whereas the area for piston B is 4 times that, at about 28 square centimeters. So we can still look at flow in and flow out. If we don't have absolute velocities, we can just use these variable V and 2V in place of a specific number for the velocity. So let's say that we stick with V and we want to find the volumetric flow in. So it would be V times the area. So 28.274 V is the flow rate in, whatever the velocity is. Whereas the flow rate out is going to have 2V because it's double the velocity in this other piston, piston A, but the area is smaller. So the net difference between the in and the out, if we do this on the mass basis, then we'd have to multiply each volumetric flow rate by the density. So the difference is positive, and that means that the liquid level is going to be rising. And then if we knew what the fluid was and its density, and if we knew the velocity of the pistons, then we could find in absolute terms what's the mass rate of accumulation inside of there. But the interpretation is that since it's positive, we know that the water level is going to be rising over time. All right, so does that make sense to everybody? All right. Now, when we were talking about control surfaces in class on Tuesday, the picture that I showed you just as a first glance was this one. And the idea was that a control surface can be stationary or it can be moving. A control surface can be rotating. It's just some place that we're keeping track of the flow in and the flow out. And so most of the time we'll do problems where the control surface is stationary. But here's an example where we may need to do something a little bit different, where we have a falling cylinder, a solid cylinder, falling through the center of a pipe that's full of water. And what we're curious to know is if the cylinder itself is falling at a velocity of 1 meter per second, then what is the velocity of the fluid that's going around the outside of that cylinder? Because what's happening is that as the cylinder falls downward, it's pushing water out of the way. And that water has to flow around the outside edge. And so try and think, visualize, as a cross-sectional view, it's going to look a little bit like this. Here's the pipe, here's the cylinder, and let me hatch the cylinder just to make it clear that it's solid, and the fluid isn't going to be flowing through the cylinder, but as the fluid goes down, the cylinder flows down, the fluid is going to be flowing up and around it out of the way. So flow rate can be a solid flow rate as well as a liquid flow rate. You know, Q in terms of cubic meters per second, that can be cubic meters of a liquid, or it can be the rate that this cylinder is entering our control volume. So what I'd like you to think about as you try and solve the idea of what's the velocity of the water as it goes around the outside edge, what we're trying to find out is if this is our circular cylinder here, and it's pushing water out of the way as it falls, what's the velocity here? What's the velocity of the water? If we assume that it's the same all the way around, what's the average velocity as it flows around the outside edge? So where would you put control surfaces to describe what's happening? You've got something flowing in and something flowing out. So before we actually start crunching the numbers on this, just in your notes, a scratch piece of paper, start with this drawing, and where would you put those dashed lines to indicate the control surfaces that something is flowing in and something is flowing out? So like in this example, our control surfaces where something is flowing in and something is flowing out, it looked like this. And what you want to do is you want to make sure that the control surfaces that you draw, it has to enclose a volume. So a control surface can't just be a plane. It has to be encompassing some interior volume. Make sure that anything that's flowing in or flowing out is going to do of interest in the problem is going to do so through the control surface that you specify. Are going to capture where something is moving. And so the cylinder is moving down. What we want to do is as the cylinder moves down, it's going to be entering our control volume. And so we want to draw a control surface that captures that entry into the control volume. And then also the fluid is going to be going out. And so if we draw a control surface that looks like this, if we draw a control surface that has this shape, then what's going to happen is that the cylinder is going to fall down into the control volume, and so that's an in, and then it's going to cause an equal volume of flow out through this control surface, and there's no change in accumulation. And so the storage term is not varying because there's no additional capacity for liquid storage inside of our control volume. It's already full of water. It's just that the cylinder goes in and the water goes out through the control surfaces. And so now we know the diameter of the cylinder, and so you can find with the diameter of the cylinder you can find the area. We know the fall velocity, so you can calculate a volumetric flow rate of the cylinder. You know, at what rate is the cylinder entering our control volume? If you know the cross-sectional area of the cylinder and its speed downward, you can find a Q in, and Q in and Q out are equal. So see if you can calculate what's the velocity of the water as it flows around the outside edge.
Is that one that?
No, you did the one where you got
Yeah, that's what it's
What
like
did
when
you
you
do?
go on the floor tire, it's like black and there's
All right, here we go. Okay, so the cylinder's falling down, it's entering the control volume, and it's pushing the water out of the control volume. You can kind of think about it as like a syringe. So, but the syringe is, the cylinder is the plunger that's going down into this volume that's full of a liquid, and so the liquid that's inside of that volume is going to be flowing out through the only escape route that it's got, which is around the outside edge of the cylinder. So we can find the flow in to the cylinder, excuse me, the flow into the volume is just going to be the velocity times the cross-sectional area of the cylinder. And so flow in and flow out are equal. Thus the velocity is going to be the difference in the two areas, the net area between the two. So the outer area minus the inner area. And we should get that the velocity of the fluid as it moves around the outside edge is going to be 1.29 meters per second. So the bigger that cylinder is, the larger the velocity would be, because there would be progressively less and less flow area and also more and more liquid volume being displaced. All right. Any questions about this illustration? In the lab this week, we talked about the orifice equation, and where there's an opening in the tank, and where by applying Bernoulli's equation at the surface of the reservoir and the jet of water that comes out, and looking at the change in elevation, assuming zero pressure at both of those locations, assuming zero velocity at the surface of the reservoir. And what we can, from that, determine is the velocity of the jet as it comes outward. We can also apply the Reynolds transport theorem to that in saying that if this is just going to be draining over time, then the height is going to be going down as there's flow out if there isn't any flow in. And so the rate of accumulation would be the mass flow rate out, and it's going to be a decrease in time. So you have a similar problem related to that in the homework assignment. And if you've already looked at the homework assignment, you maybe have seen this problem number 8. And I wanted to just give you a small bit of clarification and guidance on this problem, because we can see that there is a flow rate in through one pipe. And this is an oil where some specific gravity is specified. So from the specific gravity, you can get the density of the oil. But you'll notice that what it is coming in is a mass flow rate, and then the outflow from this enclosed pipe is going to be specified in volumetric terms because we know the diameter and velocity, the average velocity. But then there's also an orifice, and a jet of the fluid is draining out of the bottom of the tank, and of course that velocity of the jet is going to be dependent on the orifice equation, square root of 2gh. But there's a key point in this problem statement where it says when equilibrium is reached. So what is the interpretation of that when it says when equilibrium is reached?
Mass and control line, the change in mass and control line with respect to time and zero.
Exactly right. So the equilibrium means is that there's no change over time. So steady conditions. And so it doesn't come right out and tell you directly. It tells you indirectly that in equals out in this problem. Because at first it may not be an equilibrium. It doesn't matter if there's a little bit of water or a lot of water. If there's a lot of water, if this h is really tall, what will happen is that the velocity will be high from the orifice diameter. If the h is really shallow, then there won't be very much flow out of the orifice diameter. But eventually it will come to a point where, because of the head, the flow in and the flow out through both of these two discharge locations is going to be equal. And so this is saying when you finally do reach equilibrium, then what will be the height h? So this is going to be a two-step problem where you have to say, well, if in equals out, then what does that tell you about the velocity that's required at the orifice? So you'll be looking at the mass flow rate in, and you either have to convert that to a volumetric basis or you have to convert this into a mass flow basis. But either way, you want to look at the whole picture of in versus out, and then to make it equilibrium so that in and out are equal, how much flow needs to be going through the orifice. All right, so I just wanted to clarify what I meant by equilibrium. I meant steady state. Any questions about that? The application of the Reynolds transport theorem, like I mentioned earlier, is pretty important in environmental engineering. And I think some of you are going to be taking environmental engineering next semester. Some of you, sadly, won't be. But you still could, if you need a technical elective or something. For that matter, you could take hydrology. Even if you're a mechanical engineer, think about the places you could go if you were a mechanical engineer that also knew hydrology, right? So I'm just saying. So anyways, in environmental engineering, one of the important processes that has really changed things throughout the world is wastewater treatment. And in wastewater treatment, prior to about the 1950s, it was pretty common just to have really rudimentary wastewater treatment, where you'd have your waste from the sewer going into a tank, and whatever settled to the bottom or whatever floated to the top, you'd skim that out, but everything else would just go straight to the river. And so that left all of the waste that was dissolved in the water would go into the river, and that could cause a lot of problems with a reduction in oxygen in the river. And it seems like, well, who really cares about that? But if you don't have dissolved oxygen in the river, then the anaerobic degradation of waste is it has a horrible smell. It forms hydrogen sulfide, which is a poisonous gas that's toxic. It can kill fish in the river. So it was pretty common to see downstream of major metropolises just huge fish kills having to do with the sewer treatment. So the big innovation that changed that was the process called secondary treatment of sludge. And so what you'd do is you'd pump sludge from the bottom of a clarifier and you'd put it into an aeration basin, and so then that would begin to remove the dissolved solids as well as the ones that were just suspended. But one of the tricks of doing that is that the bugs that are living in the secondary reactor require pretty steady flow of air and food. Microorganisms can't just be turned on and off like a switch. It's not like a pump where you can just push a button and then the pump is operational. The microorganisms take days and in some cases weeks to become fully established and to colonize a wastewater treatment plant. So if you think about how wastewater is generated, it's generated by people washing dishes, taking showers, flushing the toilet, and all of those things vary quite a lot over the course of a daily cycle, where in the middle of the night, if you're asleep, you're not using water. Maybe you have a small drip from your foundation drain that's contributing some base flow into the sewer treatment plant, and there might be some industrial operation where the people are working all night long, and so there could be some flows from that. But residential flows are highly variable, where there's a big change over time, where the daily average flow isn't necessarily going to be the same as the low flow rates at night and the high flow rates during the day. And so these bugs, which need a steady flow of food and oxygen to be most efficient, are really at odds with the way that we generate wastewater. And so one of the applications of the Reynolds transport theorem is in sizing a flow equalization basin. And so to make sure that this process is smooth, it's pretty common to add a flow equalization basin. It's just basically a big storage tank, so that during the night, when the inflow is low, you can draw from the flow equalization basin and make up the difference between how much flow is coming in and how much flow you need to be providing to the microorganisms in the aeration basin to keep them happy and productive. And then during the daytime periods, when there's more flow coming in than your treatment plant can handle, then that storage tank would be filling. And so it's this daily cycle of filling the flow equalization basin at night, during the day when there's more in than out, and then during the nighttime periods drawing down the flow equalization basin. And so that's one application that's pretty common in every city that has wastewater treatment. They're trying to look for ways to optimize and improve the efficiency of those bacteria, and equalizing the flow is one important way to do that. Okay, that's all I have for you today. Last time I stole some of your time, so today I'm paying it back with interest. Just to reiterate, the homework number 8, that's due on Tuesday before class, and so as you're working through it, let me know if you've got any questions, and I will see you next week.
Hey, on the engineering econ project, if we get value